Good afternoon, everyone. Thank you for joining us. Welcome back. We are glad that you're here. 730 subscribers. We're very thankful for that. I'm Steve.
Yes. And I'm Scott. And yes, we are. That is, we appreciate it very much for you guys listening and subscribing. So
together, we are Backyard Musings, the science and technology channel.
Yep. And we're talking about another topic in space today. Or this afternoon. So here we go.
Data from Parker Solar Probe is helping scientists uncover how solar wind is heated and accelerated, improving predictions of space weather and deepening insight into plasma behavior around the sun and beyond. So remember, Scott, we did some reports where like a solar flare affected the satellites around our planet. Remember that? Like there was serious concern that we'd have disruptions down here on Earth. Do you remember that?
And almost all of our communications are based on satellites flying around in the sky, floating around in the sky.
Yeah.
So that we would be in deep doo-doo if that ever happened.
So
we would not be able to do what we're doing right now.
Right. Close-up measurements from NASA's Parker Solar Probe are giving scientists an unprecedented look at how the solar wind gains energy and speeds away from the sun. These insights are sharpening space weather forecasts. You heard that right, space weather, and expanding scientific understanding of how hot electrically charged gases behave near stars and throughout the system. Would you like to know more?
The results, published in Geophysical Research Letters on January 29th of this year, address long-standing questions about how energy and matter move through the heliosphere, the vast region shaped by the sun's activity. This space environment extends far beyond Earth and the moon, influences every planet in the solar system, and reaches into interstellar space. Changes within this heliosphere have also triggered powerful space weather events.
Yeah, we've just talked about that.
Yeah.
One example is a coronal mass ejection, when the sun hurls massive amounts of its atmosphere into space. These eruptions consist of fast-moving charged particles that can collide with Earth's magnetic field, disrupting satellites and radio signals. They can also increase radiation exposure for airline passengers on polar routes, said Christopher Klein. Because the magnetic comes from the poles, so the poles will be the weakest protected. So this was, according to Christopher Klein, associate professor in the University of Arizona. It's not Arizona State, University of Arizona Lunar and Planetary Laboratory.
Although it may be difficult to picture the sun having an atmosphere, since it's essentially a churning sphere of plasma made of hot ionized hydrogen gas with no solid surface, decades of research have revealed a detailed internal structure. At the center lies the core, where hydrogen atoms fuse into helium, producing the energy that powers the sun and radiates outward into space. Again, another sign of a higher power's influence, right? And
this is not by chance.
Yeah, definitely not.
Surrounding the core are several layers, with the outermost forming the sun's atmosphere. The photosphere is the visible layer where sunspots appear. Above it sits the chromosphere, a thin region that can produce solar flares and creates the mottled appearance seen through specially filtered telescopes designed for safe viewing. Beyond that lies the corona, a faint halo of plasma that is normally hidden by the sun's intense brightness and becomes visible only during a total solar eclipse.
Since its launch in 2018, Parker Solar Probe has traveled closer to the sun than any previous spacecraft. Following a complex flight path that includes 7 gravity assists from Venus, the probe reached its first closest approach on Christmas Eve 2024. These repeated close encounters have allowed scientists to chart the sun's outer boundary in ways that were previously impossible.
One of the biggest puzzles sits in the sun's temperature pattern. Plasma cools dramatically on its way outward, dropping from about 27 million degrees to around 10,000 degrees Fahrenheit. That's a severe drop.
That's pretty hot, yeah.
In the visible photosphere. Then somehow heats back up in the corona to more than 2 million degrees.
Wow. This unexpected heating is driven by complicated interactions between charged particles and intense magnetic fields that twist, stretch, and sometimes snap back into place. Despite decades of study, the details of these processes remain unclear and continue to challenge heliophysicists.
Before Parker Solar Probe made its daring close pass, sometimes described by the mission team as kissing the sun, scientists had limited information. The spacecraft's closest flyby brought it within 3.8 million miles of the sun's surface. Before that, researchers relied mainly on simplified assumptions about how charged particles were distributed in space.
So 3.8 million miles away, and it's flirting with disaster. That's pretty crazy. To answer how the solar wind has heated that, Klein's team developed a numerical tool called Arbitrary Linear Plasma Solver, or ALPS, which can analyze the actual particle distributions measured by Parker rather than forcing the data into idealized shapes. That lets researchers calculate how waves travel through the plasma and how the heating rate changes as particles stream outward. At the point of no return, where the solar wind breaks free, the particles start cooling, far more slowly than simple expansion would predict. Klein describes that slower cooling as dampening, a key clue that still needs a full explanation. Okay.
By combining ALPS with Parker's observations, the team can precisely measure how energy is shared among different types of charged particles in the solar wind. Klein said this capability reshapes understanding not only of the sun, but also of many other cosmic environments shaped by hot plasma and magnetic fields.
Okay.
Pretty interesting.
Yeah, studying the sun. That's, 3.8 million miles and away from that. And of course, we know how hot it gets when we're outside in the middle of August, and we're farther away. Yeah, what's that?
We're gazillions of miles away.
Gazillions, yeah, exactly. So anyway, this is interesting story. So
all right, folks, thanks for joining us. We'll catch you in the morning.
Take care, everyone. Have a good day.